in like very hands-on. By graph, you might think it's something like your x-y axis graph which you have in school and some line, but it is not this graph. Mathematicians use graph for another, like they use the word graph for another thing which you commonly associate with something called networks. So think of a person A, person B, and person C. If person A is friends with person B, we draw a line between these 2 points. If they are not friends, then we don't draw a line. So graph theory is a way of encoding relationships between objects. And this is a field of math which is very different from your normal stuff you do in school. Like there is no triangles, geometry and stuff, and there is no like equations like quadratic equations and stuff like on the face. And this has a lot of applications. Suppose A, B and C are cities and we want to make a road network between them. We would like to know which kind of, like, this is a very simple example, there are only 3 points, but if there are like 10 cities, then there will be a lot of overlap, like we're just making 5 cities, right? If I have something like this and I want to connect A and C, should I make a road like this, or should I make a road like this, or should I make a road like this? These are questions one can ask, and these are the kind of questions we try, like we will see which road will be the best. So graph theory developed from this one problem in Russia, Germany, somewhere. I don't exactly remember. But the point was there were many bridges in the city. So the city had many islands and bridges which connected those islands. So the question was, can I travel on every bridge? So can I, suppose I'm starting from here, can I travel on all the bridges and come back to this place by traveling on each bridge only once? Like only once on each bridge. Do you think it is possible to start on anywhere on the city and then come back to your starting point by traveling on each bridge only once?
He's asking you a question.
It's fairly obvious that you can't do it. But why is that? Like, can anyone give a reason behind why will that be the case?
Glacier started and can't go to that place by connecting other islands.
Yeah,
There is only one island which is connected to it.
that is true. What if I start from here? Is it possible?
Yes.
Okay.
No.
Again, same problem will
Yes,
come with this, right? Let's remove this. Is it possible now?
No.
What is the problem now?
Between those two.
There is only one.
Yes.
So the problem here actually is that this island has odd number of bridges connected to it. Same was the problem here. We had an odd number. Here there is no problem because there is an even number. I can always come inside and I can always go out. Right? So now one thing we have noticed is if we want to travel once on each bridge, we want all the, so we will call these vertices. This is the vertex, this is a vertex, this is vertex, vertex. Vertex is just a word for point. So we want each vertex to have an even number of neighbors, right? So we have one criteria which is each vertex even number of neighbors. But now the question is this criteria enough? Like if I had a city with islands like this, and if every island had an even number of bridges coming out of them, would it be possible for me to travel on each bridge once and come back to that place? I can't guarantee that directly, right? How would we guarantee that to someone? That is a question we can ask. And this was a pretty, like, we don't know how do I approach this, how will I solve this? Like, there is no direct way to say what to do, how to approach this. So in the 1700s, this mathematician called Euler, like you hear his name many times, like a very big mathematician, he solved this problem and he said that this is enough. Having even number of neighbors on each vertex is enough to find a path such that you can travel, once on each bridge and you can come back to the original point. And such a cycle is called an Eulerian cycle, named after the mathematician Euler. So we can see that why this would be, like, here clearly it is useful in a case of a city, where if you want to design a better city, that I want to come back to this point, we might want to have each part of the city to have even number of roads coming out and even number of roads coming in, so that one road doesn't get congested. There are multiple ways, right? So this is one clear application. But there is another thing we can ask about this. Can I travel in can I go through all islands without can I visit all islands without visiting one island more than once? Did you understand what I said? Is it possible in this case? No. We would at least have to visit one island twice to visit all islands, right? So that question is an extremely hard question that no one else has been able to solve. I mean, let me clarify better. So, if this is some graph and these are all vertices. Given any graph, does there exist a cycle such that I can visit all vertices without visiting any vertex more than once? Is a question which has not been, which we don't know the answer to in general. Like in this case, we knew if every vertex has an even number of edges, then there exists an Eulerian cycle. But the second type of cycle, we can't guarantee it exists given any condition. Like we need to check by hand every time. Or if I start from here, I go here like this. So this is an example of a very hard problem in mathematics, and they have classified it as a very hard problem. And they are trying to prove the fact that it is a very hard problem. And again, it is very clear that why would anyone care about this? Like, I want to visit everywhere in a place, in a city, without visiting one place twice, just to save my fuel, for example. Or like, I don't want to waste my time. Or a more complicated example would be like how internet networks work. So, internet is like bunch of computers connected to each other, and if data is being shared from one point to the other, we would like to find the shortest path between two computers, like the shortest number of connections. So suppose these are some 6 computers, we would like to find the shortest path between two computers and the shortest path to get back to this place such that we visit all the computers, right? And this is the question a lot of computer engineers and all care about. And we want to be able to solve this, but have not. Like, which kind of networks will guarantee a solution where I can always get back to my starting point without visiting any other computer twice? So I'll come back to this question again later. I'll just mention one more thing. So a cycle where a cycle is a collection of paths such that you come back to the starting point, where I visit every vertex only once. It's called a Hamiltonian cycle. So just a fancy name, you don't need to remember the name or anything. I'm just telling the name for the sake of it. But We can now try proving the first fact. But if any graph has an even number of, if in any graph each vertex has an even number of neighbors, then there exists a Eulerian cycle in that graph. Now to prove this, I will use two things. One is called a method of induction, which you will encounter many times in math if you have not encountered it again right now. So induction is like climbing a ladder, an infinite ladder of some sorts. It says that if I am able to climb the first step of the ladder, then I can climb any number of steps above it, or not exactly that. If I am able to do the base step, the first step, and if I'm able to carry, like suppose a 10th step, and guarantee that I will be able to carry, like climb up to the 11th step, then I am saying that I can go till any infinite number of steps. Is this confusing? I will try giving a better example. So for in this case, let me represent the graph, like the object, the graph with the letter G. So G represents some graph like this. It is some graph. And how many edges does this graph have? 5. Right? So what I am going to do now is show that for the base case, when a graph has 0 edges, that condition is true. Then I will assume that for any number of edges, suppose I'll write some letter k. For k number of edges, this is true. I will assume this. For k and below, then I will show that it is possible for any graph on k plus 1 edges to have an Eulerian cycle. So I will first show this, we will assume this, and then we will show this. And this is enough for us to guarantee that for any number of edges, this criteria will be true. Does this make like logical sense? So when a graph has 0 edges, it is just a point, right? So by virtue of it having no edges, we have considered true. You might think I am cheating, but this is the base case and it's just very easy. Now before moving on to the any number of edges case, that is k or like suppose 10, right, any number, we will do a small question, that is, if every vertex in graph has 2 or more neighbors, there exists a cycle in the graph. Did you understand what I wrote here? Think about this for like a minute or two and see how would you try showing this, if it's true or not, or like if it's true in your head or not. Does anyone have any idea of how can I show that this is true? Like some idea. But do you feel that it will be true though?
Any questions?
Something like that.
You are showing like a triangle is the smallest cycle that can exist.
Every
vertex can have two.
Okay, every vertex can have two. But then, how will we guarantee that this is connected to this point? Because this might be connected to this, and this might be connected to this, and then this might be connected to something else, and so on, right? But that's not a bad idea. We'll have to generalize it because we need to consider all cases, right? And we would like to prove this for all cases. So, suppose a graph G, like this, I'm representing it with G, has n number of vertices. N can be any number. Think of it as 10, for example. So n vertices, and I'm labeling them 1 to n. So like vertex 1, vertex 2, vertex 3, vertex 4, and so on. Fine. Now there will exist a path between any 2 points of the vertex. Right, because these are always connected. So if I take any 2 points, there is always some path between them. Right. So we take the longest path in the graph. So let this be some vertex 1 and vertex n, suppose, and the longest path in the graph between them. Fine. Now in this path, one is going forward. Right. This is one edge, and since this is the longest path, this can't be connected to any other vertex later on, right? Because that would later then become a longer path, and we are saying that this is the longest path. So this can't be connected to a new vertex. So this can't be connected to a vertex which is not here. So if it is connected to any other vertex, this vertex must be here, like before Vn. Like it must be on the path between the first vertex and the nth vertex. Fine. And that is enough for us to show that there is a cycle, because this vertex has an edge, has greater than 2 edges, right? So it has one edge between its most nearest neighbor and one edge somewhere behind, right? And there is a path like this. So this is the cycle we were looking for. Does this make sense, or are you all confused? So we have shown that there exists a cycle in any graph with 2 or more neighbors. And here we have used a maximality argument where we use the fact that there is a longest path in a graph, and then there can't exist a path longer than that. These kind of arguments you will use a lot of times in math. Like you choose an example and then use the key property of that example, like the longest or the largest or the smallest and stuff like that. So this fact will now be used to show the Eulerian cycle. So remember earlier that I had said that I assume for some number of vertices. So let me assume for some k number of vertices. K can be any number. Any number. I will assume that there exists a Eulerian path. This is my assumption. And now we want to show for any graph with k plus, this is k number of edges. Right. Number of edges. Any graph with k plus 1 edges and each vertex has even neighbors. I'm just writing neighbors with every. They have an Eulerian path. So consider some big graph on k plus 1 edges. graph have even degree. And from the earlier thing that we showed, since each vertex has even degree, that means it has a multiple, it has a degree. Oh wait, I didn't explain the term degree. Sorry. Each vertex has even number of neighbors, right? And even number of neighbors means it is a multiple of 2 or more neighbors. Right? It's a multiple of 2 as the number of neighbors, and that will obviously be greater than or equal to 2. Fine. So, vertex has even neighborhoods, that is greater than or equal to 2 number of neighbors. So this guarantees that there exists a cycle in the graph. This guarantees that there is a cycle in graph. Fine. For example, in this example, the cycle is this one. What we do is we will delete this cycle. We will not care about the cycle which exists in the graph. So in any graph on k plus 1 edges, there will exist a cycle which we will now delete. Now when we delete that graph, we get two smaller graphs, right? One here and one there. So a smaller graph will have k or lesser the number of edges. And we have assumed that in any smaller graph there exists an Eulerian path. So in this smaller graph here there is an Eulerian path, and in this smaller graph there is a path. So what we will do is we take the path from this one. We take the path from this one and we bring back the cycle which we have deleted and we combine it with the cycle. And after doing that, we took these two smaller paths, right? The smaller Eulerian path, the first one, and the small path, second one. We took two small paths and the path that we deleted, and we combined all of them. When we combine, we get a new cycle. Which is the Eulerian path in the graph with k plus 1 edges. So, using the fact that smaller graphs have a guaranteed Eulerian path, we were able to show that larger graphs will have an Eulerian path. So, now we have shown the fact that if any graph has vertices with even number of neighbors, then there exists an Eulerian path. And now we have solved our problem which mathematicians had not been able to solve for like quite a while in 17 and 1800s. Did you all understand how to do this? Okay. Would you like me to explain some part again?